And after, so some of the integrals that we did in chapter 5, when you do it again with power series, it's going to be really cool. Or that's the idea. We hopefully that you'll find it really interesting. It's just another way of doing things like that, and you'll be like, wow. Hopefully you'll be like, wow, that's really interesting and really sophisticated. Yay. Okay, a way of doing things with power series. Okay, so first off, if we're going to do power series, then we got to start with sequences first. So let's talk a little bit about sequences. So sequences, here's the definition. So this is the definition of the limit as n goes to infinity of a sub n equals L when complex numbers. And so essentially it's the same as the definition in real numbers, except that the absolute value is replaced with modulus. So it looks really the same because, absolute value notation is the same as modulus notation. So it really looks the same. So this is an epsilon capital N argument. Okay, so this definition means that given epsilon greater than 0, there exists an capital N such that if little n is bigger than that, then all the terms of the sequence are within within epsilon of L. The distance between a sub n and L is less than epsilon. Okay, that's that part. So let me give you an example of that. So let's do this. Let's prove. I'll show you how to prove a sequence. So I'll prove that the limit as n goes to infinity of 3i n squared over n squared plus 1. Okay, what do you think that limit's gonna be if it's 3n squared plus 1?
3i.
Yeah, that's going to be 3i. So let's prove it though, okay? So proof. Okay. So the first step in these kind of limit proofs is almost always to let epsilon be greater than 0. And what I like to do is scratch work. Okay, so essentially what happens is I'm going to do the proof right here, but the thing is, I have to come up with a value of n. I have to say some way of choosing n. Okay, so I have to choose n in some way, maybe greater than something that's going to make the rest of everything work out. Okay, and I want to do a string of things. In the end, I want to get this right here. Okay, so I need to get my f of n minus, I need to get an minus L less than epsilon. Okay, that's equivalent to that statement. So this is what my goal is down at, which is this. Okay, this is what I want. And I have to say what kind of value of n will get that to me. And so it's not that clear right now. I can't just right now write down a number of value of n. Or maybe if you're really experienced at this, then maybe you would know what value of n would work, right? But maybe not. Okay, so maybe we should simplify this a little bit. Maybe get a common denominator. And let's see, if I get the it's just multiplying this by n squared plus 1 up numerator and denominator. So that's 3i n squared minus 3i, right? And then those guys cancel. And I'm left with the modulus of 3i, but that's the same, or modulus of negative 3i. That's the same as 3 over n squared plus 1, right? Because now this is a real number. It's real and positive. So now I can take the reciprocal. And that flips the sign, right? Let's see, multiply both sides by 3. This is a little bit tricky. If you put a -1, that's fine. But technically, you probably shouldn't. Just take the square root. And it sounds kind of weird, like, wow, why would you? You're like, Brother Hurst, don't you know what's about that 1? Why are you just dropping the 1? Okay, and the thing is, if it was a -1, then definitely you need to keep it and play +1 over here. But the thing is, what you need is for these arguments to run up this way. Okay, and so if this is greater than, if n squared is greater than 3 over epsilon, then surely n squared plus 1 is going to be greater than 3 over epsilon, right? This does imply that. That doesn't, the implication does go this way. It doesn't go down, but it goes up. And that's the direction you need that implies. Because what's going to happen now, I have down here, this is the key right here now. If I choose n to be greater than the square root of 3 over epsilon, then everything's going to work out. Okay, so if I choose that, then n greater than n implies that n will be greater than the square root of 3 over epsilon, which implies that n squared is greater than 3 over epsilon, which implies that n squared plus 1 is greater than 3 over epsilon, which implies, and you can skip steps if you want. I skipped that step, skipped going from there to there. I just went from there to there directly. And probably people would be able to see that. And then, let's see, what do we got here? We have go from there to there. That's just multiplying by an I right here, making it negative. And then these two things are going to cancel out. So you can see that this right here is just going to simplify down to that. Okay, and you're done. That's the proof right there. Was there any part that you have found hard to follow? I'm sure probably found the whole thing hard to follow. But any part in particular that doesn't make sense to you? Anybody? Okay, so let me go over here really quickly and show what we were supposed to do. Show the elements of what we were supposed to do here. Okay, so that the proof is let epsilon greater than 0. Choose And then what you're supposed to do, choose an n such that n, if little n is this is it right here, greater than or equal to big N, that implies a sub n minus L is less than epsilon. So I guess technically I should have done that. Greater than or equal to. But then again, some books have that as a definition where it's greater than or equal to n, and other books it's just greater than. It just doesn't really matter. Doesn't matter one way or the other. Okay, so that's the idea right there. You're supposed to choose an n, a capital N, so that n greater, little n greater than implies that. That's how you prove that the limit is n goes to infinity of a sub n equals L. Okay, let me show you something else really quickly. Prove that the limit is n goes to infinity of I to the n. Do you guys know what D and E stands for?
Does not exist.
Whoa, nice. Yes, does not exist. So we're supposed to show that that limit doesn't exist. And this is really tricky. At first you think, oh, this is really easy, right? But showing it is really easy, that's for sure. Because what happens? So if a sub n is I to the n, then when n equals 0, we have 1. When n equals 1, we have I. And then when n equals 2, we have -1, and then we have negative I, and then 1, and then I. It just goes like that, right? That's what it's going to look like. So that's what the series is going to, that's what the sequence is going to look like, right? And so sounds like really easy to prove this, but if you look at the definition, it becomes a bit more complicated because we not only have to show, so like you could say, oh, I can show that it doesn't converge to 1 because there's all these other values that are far away from 1, right? Or I can show that it doesn't converge to I because all these other values. And I can show that, or you can show that it doesn't converge to -1 or so on, but then that's kind of missing the point because you have to show that it doesn't converge to anything. That there's nothing that this can converge to. So that makes it a little bit harder. I guess I don't necessarily want to spend a whole lot of time with this, so I will kind of run over an outline of what's going on. Basically, this function hits 1, I, -1, and -I, right? So you have to show that, so let's do this. Let's let L, so this is what the proof would look like. Proof. Let L be a complex number, any complex number. I don't care what, any complex number. And we'll show that the limit is not going to be L. So here, what you can do is you can choose epsilon to be, if you look at these points, they're all, let's see. Let's just take these 2 points here, 1 and -1, just those two. The distance between those is 2, right? So let's let epsilon be 1. Okay, we'll just choose epsilon to be 1. And we'll show that this can't work. And then one way that you can do it is you can say case 1. is that the real part of L is greater than 0, greater than or equal to 0. So that means you're over here in the right half plane. That means that the distance between 1 minus L is greater than 1, which is epsilon. We've chosen epsilon to be 1. And so 1 minus L is greater than 1. So at the same time, we probably should have said let n be a natural number as well. So let L be a complex number and let, wait. Choose epsilon greater than 0. Let let n be any natural number. Well, there exists an n greater than capital N, such that I to the n is equal to -1, right? No, is equal to, wait, this should be a -1, I'm sorry. Okay, so this set right here is everything over here, right? So the distance between this point and any point over here is greater than 1. It's greater than epsilon, the epsilon value of epsilon that we've chosen. Okay, so that means that I to the n minus L is greater than epsilon. Okay, and then we could go case 2, where the real part of L is less than 0. Okay, so that one would be everything over here. And then we could argue the same thing. There exists an n greater than n such that I to the n equals 1. And in that case, that's also going to be greater than 1 because you're over here now. The distance between this point and any point over here is greater than 1. Okay, and so then the limit then goes to infinity of I to the n does not exist. Okay, so that's how you would prove that, or a rough outline of the proof. Okay, so let's move on. You have this proposition about limits, which is pretty straightforward. So here, this is multiplying by a constant, and also adding, and then this is multiplying of two sequences, the quotient, and then also n plus 1. Whether a sequence converges or not doesn't depend on the first terms. It depends on the n. What happens is as you go to infinity. So you can take whatever number of finite terms, and that's not going to affect whether the sequence converges or not. It's what happens at the end as you go to infinity. Okay, if you have a continuous function f, then the limit is equal to the limit of that. So what this is saying is, let's suppose that we had f of x equals x squared over, actually it should be z, I'm sorry. No. Wait. Yeah, it should be z. I'm sorry. So f of z, so let's suppose we had f of z equals z squared plus 7 over I z squared, okay? And we know that as that the limit as okay, hold on a second. It was x. So you know that the limit as x goes to infinity of f of x is what? It's 1 over I, right? Or negative I. So that means that the limit as n goes to infinity of n squared plus 7 over I n squared, that's going to be negative I. Okay. So it's basically, if you have the x's here, and you're taking the limit as x goes to infinity, you can replace the x's with n's, and you're going to have the same limit either way. That's all that last part saying right there. So that's if your f is continuous. Okay, if your f is continuous, then that's how that works. Okay, let's see here. Also, any bounded sequences is any bounded monotone. Wait. Any bounded monotone sequence is convergent. Okay, monotone means it's either increasing or decreasing, or non-increasing or non-decreasing. Is what monotone means. So if you're monotone, that means you're always. It's like if you're monotone increasing, that means you're always getting, the terms are always getting larger. And if that's the case, then, and then if you're bounded, then you're going to have to converge to something. Likewise, if you're monotone decreasing. Now, there's another important, there is an important concept that I couldn't find where the book covers it. Oh, I know what the problem is. There we go. I don't think the book covered it that much. I couldn't find where it covered it. Maybe it does. But to converge, you need both real and imaginary parts to converge. Okay, so you have to have both of those parts converging. Okay, so for example, let me take a sub n equals 1 over n plus I times 1/2 to the n. Okay, this one is going to converge. You know that the limit as n goes to infinity of 1 over n, that's 0, right? And the limit as n goes to infinity of 1/2 to the n, that's also 0, right? So this one is going to converge to 0. Now you can think of it like that. You can split it up. If you can split these up into real and imaginary parts, then great. And that's going to be 0. Okay, another example would be, okay, let's suppose that you had n plus 3n over n plus 1I. Okay, what's the limit as n goes to infinity of the first one, of just this one? That's going to be infinity, right? Okay, what? All right, but I'll make you guys answer this one though. What's the limit of the imaginary part?
3.
Yeah, that's 3. Okay, so this one though, does not exist. Or we could say it diverges. Or we could say that it diverges to infinity. Whichever way that we're feeling in the context. Because this part goes to infinity, right? Okay, another example would be something like this. Wait, I want to do green again. Okay, so what do you think this one? What do you think this one's going to do? It's -1 to the n plus 2i. What do you think? Diverges or converges to something? What does -1 to the n converge to something?
No.
No, this one. This diverges. This one, on the other hand, converges. But the whole thing diverges. Okay, diverges because the real part diverges. So to converge, you need both the real and imaginary parts to converge. Okay, and maybe one final example would be, let's see, what color? I'll just do, no. Would be maybe e to the pi over n I. So that could be another example. Now this one you could say right at the bat, as n goes to infinity, this goes to 0, right? So you could say that limit as n goes to infinity of e to the pi over n I is going to be 1, right? Because as n goes to infinity, this goes to 0, so it's e to the 0, which is 1. But you could also split it up into this. It could be cosine of pi over ni plus I sine of pi over ni. And then, wait, there's no I there. Okay, so cosine of pi over n plus I sine of pi over n. You can split it up that way. And then say this one goes to 1 and that goes to 0. Okay, because cosine of 0 is 1 and sine of 0 is 0. And so that's going to converge to 1. Okay, so there's that idea right there, that you can check convergence by looking at the real and imaginary parts of the sequence. Okay, and then this right here is important. Archimedean property, that's important for doing proofs, because, and I basically use that. Essentially, if you have a real number, then there's an integer that's greater than that. No matter how big your number is, there's an integer that's greater than that. And you can do that by just rounding up and adding 1 or something. You can always take a real number, round it up, and add 1. Or round it down and add 2. Whatever you feel like. And that's, I definitely use that right here in this part of the proof. So I found this, the square root of 3 over epsilon, right? Epsilon's a positive number, so that means that this right here is a real number, and I can choose an n that's greater than that. So I just use the Archimedean property in that proof. Okay, so that's why this theorem 7.6 is useful. And they don't go to proving that, because then that would kind of take us out of what we're trying to do in this book. Proposition 7.7, this is something you already know. Exponentials beat polynomials as far as going to infinity. So if you have like c to the n, that's going to get wiped out by, or I'm sorry, if you got like c to the n where the modulus of c is greater than 1, that's going to wipe out any polynomial. Okay, factorials beat exponentials. So if you had c to the n and then you're taking n over n factorial, that's going to be 0. Okay, so those are things from calculus, like calculus 2, when you're talking about sequences in series. It really just kind of goes over to that. Okay, so let's talk about series. And here's the definition. So the series, you're kind of adding up a bunch of numbers. You're adding up the terms of a sequence, really. And so the partial sums are these, where you're just adding up to. So a partial sum are really important. And they are just adding up a certain number. Up to a sub n is equal to k equals 0 to n. So you're adding up just the first n plus 1 terms of the sequence. That's the partial sum. And the series, which goes from, I'm sorry, let me use k. The series is equal to the limit of the partial sums, okay? Which the partial sums are these right here. Okay, so the series is the limit of partial sums, and this is what was taught in calculus, but some people might forget it. I found that a lot of people forget that. Maybe it's because it's really painful or something. Okay. If your terms are real, then the series converges if and only if the partial sums are bounded. There are a few different examples of different series. And let me go through some of these. Okay, so first of all, a really important example is the geometric series right here. This is probably the most important one. This is probably the most important concept of this section, because it's going to come up in the future. Okay, so if you let me do it on this page. What did I just? Whoa, I circled that and then I just erased everything. Okay, so the geometric series. Okay, so this is one of the forms of the geometric series, but the one that I want you guys to remember more would be this one here, where you're starting from 0 to infinity of z to the n. Okay, that's going to be equal to 1 over 1 minus z if the modulus of z is less than 1. So just like the series with real numbers, you're going to get this if you're if r is like you have a r to the n, it's 1 over 1 minus r. You might remember that. That's true if modulus of r is less than 1. If modulus of r is greater than or equal to 1, then this is going to diverge. Okay, but this carries over to complex numbers. And it's kind of interesting because this right here, modulus of z less than 1, is going to be this disk right here of radius 1. Okay, so this is a really important series. The power, it's the basis of the power series, which is what we're going to be looking at in this section. Now, also along these lines, if you have, I guess I should have made those Ks. If you have a series like this, wait a minute, no, that's what I want to do. Like that. If you have a series like that, which is k equals 0 to infinity of a sub k, then you can compare it with a geometric series. And what happens there is you let L be the limit as n goes to infinity of a sub n plus 1 over a sub n, but modulus of that quotient. Okay, so if that exists, which sometimes it doesn't exist, but if this exists, then that leads to 3 possibilities. If L is less than 1, then this series is going to diverge. If L equals 1, then no conclusion. And if L is greater than 1, then it will, wait, what am I doing? What am I saying? And nobody stopped me. If L is less than 1, it's going to converge. And if L is greater than 1, it's going to diverge. Okay, so you guys remember this test? Do you guys remember what this is called? The ray. You guys don't remember? Ratio test. No one remembers the ratio test? Come on. Well, I guess you guys didn't take calculus from me, so that's okay. If you take calculus from me, then my feelings would be very hurt right now. Unless nobody's like, everybody's too shy to admit it. Oh well. Okay, so let's take it, so what do you guys think of this? Let's suppose we have I plus 1. I guess I should say 1 plus I, because let's put the real part first, right? And let's say that's all over 4, and I'm taking out to the nth power, and I'm going from n to equals 0 to infinity. Okay, so what do you guys think? Is that going to converge or diverge?
Converge.
Yes, that's going to converge. And what is it going to converge to? Because this is, modulus of this is less than 1. Okay, so modulus is less than 1 for this one, because this z is 1 plus I over 4. So it's going to converge to 1 over 1 minus this. I guess we can multiply the numerator and denominator by 4. Well, look at that, 4 over 3 minus I. But of course, you can't leave it that way. So you have to multiply by a fancy form of 1, which is 3 plus I over 3 plus I. And that is going to give you, what, 9 plus, it's going to be 10 in the denominator, and the numerator is going to be 12 plus 4I. So 6/5 plus 2/5 I is what that converges to. Okay, how about 1 plus I to the n? Okay, what do you guys think that one's going to be?
1 over 1 minus 1 plus I.
Did you check this first?
Hmm?
Did you check that?
Just I. It's gonna be I or
Wait, it's what? Is it square root of 2?
negative I.
What? Isn't it the square root of the first one, the real part plus the imaginary part squared?
Yes.
That's greater than 1. So that means diverges, doesn't converge. How about this one?
It is still diverges.
Yeah, this is going to diverge. Okay, and so this one, you know, because it's like, it's adding, so you can think of it kind of like this. It's 1 plus I plus a negative 1 minus I plus 1 plus I. And so it's just kind of all over the place. And so no, it diverges. Well, not all over the place, because it's only it's gonna this partial sums are gonna bounce between 4 different values. Okay, so that's the geometric. That's a bunch of things about the geometric series, and then this is about series in general that maybe you can use a ratio test. We'll talk more about the ratio test in the future sections, though. Another thing that I would want to point out is wait, where am I? I want to review a few things from I need to review a few things from calculus. Okay, so review from Calc 2. Okay, so if you have a series like this, when do you know if this is convergent or not? This is called a P-series, right? And when does it converge?
when b is greater than 1,
Yeah, when p is greater than 1. And it diverges.
when a is less than or
Yeah, diverges when p is less than or equal to 1. Okay, so that's really important to remember. And if you have this series, in particular, if you have this series here, 1 over n, what does this one do? It is divergent,
Mm.
and it's called the harmonic series. Because it's a special case of the p series where p is equal to 1, right? And the p series comes from, you can get the p series by applying the integral test. So the integral test. So if you have, so this means the positive real numbers, which the 1 over n to the p would be. And so the series is going to be between that integral and f of 1 plus the same integral. So it's going to converge or diverge depending on what happens to the integral. Okay, here's comparison test, and here's limit comparison. No, here's comparison test. So here you have this right here. This comparison test. This right here is a test for divergence. And all this is really saying is that if these terms don't go to 0, then the series diverges. Okay, but as you know, even if they go to 0, it just doesn't mean that the series diverges, because here's a situation where the terms go to 0, but the series diverges. Okay, so if the terms don't go to 0, then we know that the series diverges. But if the terms do go to 0, it doesn't guarantee the divergence of the series. I mean, it doesn't guarantee convergence. It doesn't mean the opposite's going to be true. Okay, and then we have absolute convergence, which we talk about on the next page. And this one is modulus. Okay, so it's stronger than, it's the equivalent in complex numbers. But do you still say converges absolutely when we do that? Okay. Another thing I want to point out, and this is parallel to what I said in the previous section about sequences, converging of sequences. So to converge, the real and imaginary parts need to converge. Okay, so if a series, so in order for a series to converge, you need both the real and imaginary parts to converge. So for example, let's say I had this series right here. Let's say 1 over n squared minus, and we'll say 1 over 2 to the n I. Okay, so do you think this is going to converge or diverge? Well, first of all, this right here, is this converge or diverge? This is the real part. This is a P series,
Converges.
and P is 2, right? Which is greater than 1, so it converges. Okay, what about this one right here? What about the second part? Without the I. So just this right here. You can ignore the negative sign. In fact, let's just get rid of it. It doesn't, so negative, so whether it's plus or minus right here, it doesn't really matter. For this series. But what do you think? This converge or diverge?
Converges.
Yeah, it converges. Why?
Because it is less than 1.
Yeah, it's a geometric series. R is equal to 1/2, which is less than 1. Okay, so overall it converges. Overall, this series is going to converge. What if you had okay, what's this one going to do? Converge or diverge? Okay, so let's take a look at this one first. Converge or diverge?
Converge.
Converge.
Yeah, this one converges.
This 3 is larger than 1.
What about this one?
Converges as well.
The sequence converges, but the series diverges. And this is the P series. And P is equal to 1, which is less than or equal to 1. So therefore it diverges.
Okay.
So like I said, like what you got to train yourself to like look at not just say, okay, whether this terms go to 0 or not, because that doesn't guarantee convergence. So this whole thing diverges because this one, the imaginary part diverges. The real part's fine. It converges, but the imaginary part doesn't. So then the whole thing doesn't converge. Okay, so okay, if you converge absolutely, so absolute convergence implies convergence. And here we are towards the end of the section. Here we are. So we're just going to go up to here on the exam. But I wanted to point out right here, this function right here, this series right here. This is the Riemann Zeta function. It's a very famous function right here. And what happens is this converges, this series converges when the real part of z is greater than 1. And so just to, let me show you show you what that looks like. So if this is the imaginary axis and this is the real axis, and then this is 1 right here. Then this Riemann zeta function converges everywhere over here. It's like that. 1 over k to the z. This is kind of weird. So you have the z in the exponent, and it's kind of like the p series, except there's instead of a p, you have a z right there, which is ouch. And if z is like, if you're looking along the real number, the real axis, and you set values in there, that's just going to be the p series, right here. Except it's not p because it could be a point over here. Instead of a point, if it was a point right there, let's say 2, that's 1 over n squared, or 1 over k squared. P series converges. But if you're up here, then that's 1 over whatever 2 plus some value of I, k to that raised to that value. Okay, it's still going to converge, but it's going to be weird. If you're 1, it diverges, right? Because you're putting a 1 in right here, that diverges. And if you're over here at 0, then of course it's going to diverge. It's going to be 1s added together. Okay, but it converges only over here, but on this line here, it doesn't. It diverges, and then everywhere over here it diverges. So it converges, and then everywhere over here it diverges. Okay, but the interesting thing is that so obviously you can't define it this way over here because it's just going to diverge, but there is like analytic continuation that allows it to be defined over here.